Hi students, so today we begin lecture 33 in our course, and today I am going to discuss about the altitude effects on aircraft performance. So this is something which is important in terms of the power required in flight, and this power required is going to be different depending on the height you are at. I am Dr. Ranjan Ganguly. So now let us look at an aircraft at two different heights. So one of the heights is at the sea level itself, which I've shown here, and the second one is at some height h, and therefore the values of density, velocity are going to be different at these two locations. So let's say that at sea level the density is rho 0, the velocity is v0, and the power required is P subscript r. Similarly, at some height h, the density is rho, the velocity is v altitude, and the power required is Pr altitude. Now, in both these cases, let's assume that the weight of the aircraft is the same. Therefore, a same amount of lift is going to be required to balance this weight. So I can write these two equations here. So for example, at sea level, I have L equal to W equals half rho 0 v0 square SCL. So essentially these correspond to the density and velocity at sea level, and at the altitude I have L equal to W is half rho v alt square SCL. Now if you look at these two equations, you will realize that since rho 0 is different from rho, the velocities here are going to be different if you have to generate the same amount of lift in these two cases, because W is the same in these two cases, and we are also assuming that CL remains same in these two cases. So now let us look at each of these situations individually and try to derive some equations that relate power required at different altitudes. So let's start with sea level. So we had this equation at sea level, that's L equal W equals half rho 0 V0 square SCL. And I can immediately write the velocity at sea level from this equation. So that becomes V0 equals to root of 2W by rho 0 SCL. So this is going to immediately give me the power required at sea level, and this is from our previous lecture. You can essentially get this equation here. So now you of course know that W is the weight, CD is the drag coefficient, rho 0 is the density at sea level, S is the area of the wing, and CL is the lift coefficient. Now let's consider the same situation, but this time you are flying at an altitude. And so the equation that holds there is L equals W equals half rho V alt square S CL. And so from this equation, I can immediately get V alt equals to root of 2W by rho SCL. So from this equation, I can easily obtain the power required at altitude as root of 2W cube CD square by rho S CL cube. So here what's happened is that the density of air is different because you are at a given height. So again, recall that from standard atmosphere you can obtain this density. Go and look at the video on standard atmosphere, which we made many videos ago or many lectures ago in this course. So now I have these two equations. I have one equation for the sea level conditions, which have this subscript 0, and I have the second set of equations at the altitude conditions. So these are given by the subscript alt. So of course I have assumed here that CL is invariant between sea level and altitude, and then what I do is I can divide these two equations. So if I divide these two equations, V alt by V0, I get V alt equals to V0, and then rho 0 by rho to the power of half. So what happens is that when I divide these two, the rho 0 and rho get flipped because they are in the denominator, and so I get this equation here. Similarly, if I write power required at the altitude, I get this equation here in terms of power required at 0, and this comes to rho 0 by rho again to the power half. So what this lets me do is that these two equations let me essentially figure out what's the corresponding curve between the sea level situation and the altitude situation. So here you are seeing the sea level value here, some curve like what we obtained in our previous lecture. And if we take any point here, that point would correspond to PR0, V0. And if we put it in these two equations, we get the corresponding PR alt, V alt. So there is a direct one-to-one map between all the points which are present in the red sea level curve to the green altitude curve. So like I have shown here for one particular point. So this means that if I have a particular graph at the sea level, I can get the corresponding graph at the altitude level. So let's now consider a propeller plane. In the case of propeller plane, the power required by velocity curve looks like this. So this is at the sea level, and so the power available is given by this line here. Now this is often the maximum power which is available to you at that particular density. So at sea level, let's say this is the power here. So corresponding to this, I would get the V max at sea level given by this value here. So all the sea level values here are shown by the red lines and the red notation in the graph, or the red text in the graph. Now let's consider the same problem, but we have moved to a given altitude. So at that situation, all the graphs are given in green, and so you can see the power required curve is given by this, the power available curve is given by this line here, and the intersection of these lines corresponds to the Vmax altitude situation. So what has happened is that the Vmax at the altitude has come down. So this is typically the case because of the changes in the density between the sea level and the altitude condition. Now let's try to do the same thing with the jet airplane. So you recall from our previous lecture that for a jet airplane, the power required curve is similar, but the power available curve is given by the straight line here, because in the case of jet, this curve is nothing but TA into velocity of the aircraft. So because of the velocity multiplication, this essentially goes through zero. So essentially the intersection takes place at this point here. So all these lines in red correspond to the sea level situation. And so Vmax SL is going to be the maximum velocity at sea level. Now let's look at the green lines here. These are corresponding to the altitude situation. So here you see the power required curve intersects with the available power curve at this point. And so again, I get this green line here. That is the Vmax at the altitude situation. So again, this Vmax typically comes down when you go up from sea level to some height. So that's something to keep in mind. Now, one of the things which can happen is that the lower speed can also get impacted by these particular curves and by the changes in the altitude. So, for example, let's consider the power required curve at a given height and the power available curve. So remember, this is the maximum power you can get at any particular altitude. So again, of course, we know the Vmax value that's given by this line here. And there is also a Vmin value, which is coming from the fact that below this point, the available power is actually less than the required power. Therefore, you cannot really go into these regions. So this blue line here corresponds to the Vmin alt. Now, what can happen in some cases is that the stall speed may actually be lower than this particular Vmin alt speed. So in that case, what would happen is that the lowest speed possible by the airplane would be dictated from the power required and power available curves rather than from the stall speed required. Recall that in one of our previous lectures, we have discussed V stall to be root of 2W by rho infinity SCL max. So this was the equation which we can use to get the stall value. And do remember that CL max is the maximum lift coefficient which you can get, which is the highest point of the CL alpha curve. So if you are unfamiliar with this concept, go back to my previous video on this topic and take a look at that. That's something to do with the high lift devices and so on, which are often used to increase the CL max value in any given airplane. So that was the lecture today on the power required and power available curves and how they shift between sea level and at a different altitude condition. So essentially, if you have the sea level graph, you can very easily obtain the graph at the different levels. and through that means you can obtain what is the maximum velocity of the aircraft at any given height, and also what is the minimum velocity of the aircraft at any given height, which is given to you by the power required and the power available curve. So always keep in mind that you need to actually check about the stall speed, whether the minimum speed is being dictated by stall or the minimum speed is being dictated by the available power, because this keeps shifting. Both the power required and power available curves keep shifting depending on the density of air, which keeps shifting depending on the height at which you are flying. So that was the video for today. So we have covered a lot of topics which are very important in terms of aircraft performance, because one of the fundamental things you need to do in aircraft design is to figure out the power required, the thrust required, and so on, and the available power and the available thrust, because these are critical values which are required to make sure that your aircraft is actually going to fly in real life. Because if these conditions are met, then only your aircraft is going to have sufficient thrust to actually be capable of any flight. So that's something which is very important as far as aerospace engineers are concerned. I'll end this video here and I will see you in a video sometime soon. Then I think we'll start talking about the rate of climb and gliding flight. See you then.